Very quickly, there was a mistake in the homework in question number 2. I just corrected it, and it's going to be uploaded on the web. I already sent it to the assistant. The airplane is flying from north to south. Okay, that's it. A passenger airplane is flying straight from north to south at a velocity v of blah 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 with respect to an observer on Earth. La 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 la. Okay, there was something with the equator, and so that was something I copied from somewhere else, of course, from a previous work, and it was still in there. I apologize. It is simply flying from north to south. Okay, that's it. And it's the new version is uploaded on the web. Okay. All right. So there were a few questions during the break. The first one is the first question is. I remember the first one. What was the second one? I said I would explain it during the lecture. Who asked the question? Weak body and transform matrix. Yeah, that's fine. Was there one other? Yeah, but that's the same question, isn't it? Okay. All right. Remember now. The question is, do we have to memorize these? Can you close the door, please? Do we have to memorize the transformation matrices for the exam? The answer is, it's up to you. You can memorize the whole book if you want to. I mean, I cannot tell you not to memorize. I'm just telling you, you probably don't need it. I will not expect anyone to memorize anything. You should have a way to easily obtain it. Okay? Or if it is too complex, let me put it this way. I will count or add the time to the exam for which I believe you will need to, that you would need to obtain that matrix or rederive the matrix. For instance, this one here, okay? I would either ask you to obtain this matrix, so then you will get points for that, or derive it, or I will give it to you. But there will be no question where I say, this is theta dot phi dot psi dot, find P, Q, and R. And the person who memorizes it does it in 1 minute, and the person who doesn't memorize it does it in 1 hour. So this will not be a fair set, okay? I will not do that. So I will either say derive it, and then it will be in the time and you will get points for it, or I will give it to you, then everybody has it, okay? But you should know how to transform a vector when you rotate it around one coordinate system. That you should know how to derive, you see? And you should know if I get an intermediate one and then obtain a transformation matrix for the second one and rotate it again around this, you should know how to do that. How to write the numbers to rotate something around the x-axis, around the y-axis. You should know how to do it, okay? So, can you do it better when you memorize it? I don't know. I am not one of the people who can memorize things. So I would always derive it. And some people do memorize it and they are successful in some ways. But the core of the midterm questions will never be try to derive, multiply numbers and all this. It will be more, the time should more be on the thinking and understanding vectors, transformation matrices, coordinate systems, and angles and things like that. Okay? So if you don't memorize anything, you should feel safe. That as long as you understand, you'll be fine. Is that fair? Okay. Okay, so we have probably established now that P, Q, and R, theta dot, phi dot, and psi dot are not equal, okay? But they have a relation, and it's this one here, and this is the relation. So this sequence here, P, Q, and R, in obtaining theta, phi, and psi is quite interesting for airplanes. Let me just give you an example. I think this is something that might be for you to visualize a little better. See, pilots in the cockpits, they really want to know about theta, phi, and psi, right? They want to know their attitudes. Because if you are in a cloud, say, okay, you can't really tell very well what your theta is and what your phi is and maybe what your psi is if you just don't see around. Because if there's no cloud, you could look at the horizon and you can tell your phi angle, you can tell a little bit your theta angle. But even then, if it's a few degrees of change, you might not be able to tell. Okay? And therefore, you need theta, phi, and psi in the cockpit as a display. Secondly, you heard about black boxes in airplanes, right? They record everything. If there's an accident or something, everyone is looking for the black box or the data recorder, the flight data recorder. The flight data recorder records a lot of things, but it definitely records Euler angles because it will tell you what is the attitude, the angular position of the airplane during flight at each time instant. So it's here, and a second later it's like that, a second later it's like that. So you need theta, phi, and psi. In other words, the airplane has to measure theta, phi, and psi. So the question is, how do you measure theta, phi, and psi? Because theta, phi, and psi is not around a coordinate system, right? I mean, there are around axes that really don't conform a coordinate system, right? So in most applications in airplanes, this is the relation that's been used to calculate theta, phi, and psi. Because measuring P, Q, and R is a little bit more straightforward. Let me explain you why. Because if you have an airplane like this, and this is your body fixed coordinate system, x body, z body, and y body, okay? What we do is we use gyroscopes. You might have heard about gyroscopes, right? An IMU this is called an inertial measurement unit. An IMU is an inertial measurement unit. Okay? An inertial measurement unit has 3 accelerometers, but also 3 gyros. 3 gyros in the sense that in 3 axes. So it's a gyroscopes. Gyroscopes measure angular velocity, okay, angular rate. Okay, some of them measure angular acceleration, but that's a little out of scope for us right now. Let's say the gyroscopes measure angular velocity. Okay, so if you mount that gyroscope on the airplane, the 3-axis gyroscope on the airplane, you will have a gyroscope on. Let's say you mount it over here on the CG. You will have 3 gyroscopes in 3 axes that measure the angular velocity. So because you mount it on the airplane, you really measure the angular velocity along x body, y body, and z body. If you put it exactly on a nice surface on the airplane, the gyroscope will measure x body, y body, and z body. Even if you are going up like this, look up here, even if the airplane is going up like that, the gyroscope will still be measuring these things, right? The body axes. That's what a gyroscope measures. Okay, now, basically the gyroscopes actually do measure P, Q, and R. That comes out of the gyroscope. Okay, so what do you do with this? You take the measurement of the gyroscope measurement, send it to a computer or something, and let it calculate this. Okay? The inverse, of course, right? This one here. Because you get P, Q, and R, you obtain this. So you multiply it with this, and you obtain phi dot, theta dot, and psi dot. And then you take the integral of this, integral, and you obtain phi, theta, and psi. And these are your Euler angles now. Okay? And of course, for this thing to work, you take this and send it back over here. You need theta and phi for your next iteration, because otherwise this will never work, right? You need theta phi, the Euler angles themselves, in order to use that relation here. Okay? And then you have theta phi and psi, and you can send it anywhere you want. You can send it to the cockpit, you can send it to the data recorder, you can use it, you know, wherever you want, and this is, you have the Euler angles measurement. So what I'm trying to say is that the Euler angles are usually not measured directly on airplanes. What is really measured is P, Q, and R. P, Q, and R are the angular velocities along the x body, y body, z body axes. And this is so because we are taking the gyroscope, mounting it on the airplane, and if the airplane rotates, it will rotate with the airplane, so it will basically measure the angular velocities on the body axis system here, P, Q, and R, okay, the gyroscope. So you go through this, and then this. So do you see any problem with this whole story? Would this work all the time, or would there be a problem in certain situations? Or do you see a problem in the application of this? Let's say I give you a gyroscope and I ask you to apply this. What problems do you see here in this story? Yes, please.
Do we know the integral constant?
What integral constant?
Constant from integral derivation.
Where is the constant? You're just taking an integral. Do you know? You just add the previous value to the... There's no constant. You just take this and start. I don't know what you mean by constant. Yes, please.
How do we know the initial
Oh, see, that's an important question. Now we figured out one. Listen. When I first come here, listen. When I first come here, I have P, Q, and R. I come here. I need theta phi and psi. What is coming from here? So the first time I come here, I don't have a theta phi. Right? The first time I come here, I don't know of theta phi. So what do? What is my initial condition? I mean, in real life, come on, you're in an airplane. You cannot call somebody and ask for initial condition. You're in an airplane. So what is my initial condition? Yes, please.
We have to calibrate our gyroscope.
Good. So we have to initialize our gyroscopes or calibrate it, which means you start this procedure with known theta and phi. You need to know it, and you start it from the first iteration will be with a theta and phi that I know. So I need to be in a situation where I know theta and phi. That means two things. Either someone else tells me, which means there's another measurement on the side, or I'm on the ground, and by definition I know my theta and phi. And that will be my initial condition. So I need to initialize my gyroscopes, initialize my IMU. So you hear this a lot, initialize my IMU, initialize my gyro. Okay? That's what it means. You need to initialize it because in the first iteration you don't know where you are. Okay? So first, you need to initialize. Initialize my rate gyros. Okay? Yes, this is absolutely what I need to do. I need to initialize my rate gyros. Good. This is problem number one. So every rate gyro needs to initialize. IMU needs to initialize. INS needs to initialize. And that's what it means. What else? Do you see any other problem? Yeah.
I'm wondering if this feedback in this block diagram is a negative feedback or a positive feedback.
What does it mean? You mean adding, subtracting?
We get the Euler angles and we map.
So this is happening, let me just say, this is happening approximately 100 times a second. So you measure, calculate, go back. Measure, calculate, go back. So it's 100 hertz. You might have it in lower frequencies, say 30 hertz, 20 hertz, depending on the resolution you want. But usually this loop is happening at least 10, 20, 30, 40, 50 times a second. Okay? So you measure, calculate, go back, and all this. So positive, negative, I don't know what you mean. I calculate this, go back, and in the next loop, I'm using this theta phi in my calculation. Is that okay? What else? We need to hurry up. There's one more problem. I mean, come on, it's written there. I can see it. You don't see the problem? Look at the matrix. You see a problem? What happened?
That matrix is not defined for some certain angles.
For which one?
That inverse matrix.
Yeah, for which angle is it not defined?
For example, 90 degrees.
Which one is 90 degrees?
Theta not 90.
What happens if theta is 90 degrees? What is theta 90 degrees? Look up here. This is theta 90 degrees. Right? Okay, so what happens when theta is 90 degrees? It goes to infinity. Why does it go to infinity? What is tangent theta? Infinity. Infinity. You're done. This whole system will blow up when theta is equal to 90 degrees. Why is that? First of all, so that means that this cannot be used. This is not defined for theta equals 90, theta equals 90 degrees. There's something that is not okay. Not okay. Let me just put it this way. It's not okay because this R1 goes to infinity. Okay? R1 minus 1 goes to infinity because of the tangent theta. At theta equals 90 degrees, this is not defined. What could be the problem? I mean, is it just a mathematical error? Are we unlucky? Or is there something else going on? It has nothing to do with gyroscopes. It is a mathematical situation here that this, before coming to that story, you see that this is not working for theta equals 90 degrees, you see? You see that, right? It's not working. If you have theta equals 90 degrees, this relationship breaks down. There is no relationship when theta equals 90 degrees. Or you cannot write it this way, at least. Can you guess what is going on here? Let me tell you what's going on. Let me tell you what's going on. So Euler angles are great, except for theta equals 90 degrees because of this. Okay? So let's look at this. Let's say this is theta equals 90 degrees, right? Theta 90 degrees, so you're going upwards like this. So let's say this is north, east, and down, as we always do. Okay? And let's say the airplane is in this situation. Okay? Going up like that. Okay? North, east, and down. So how do I get to this? One rotation around psi, one rotation around theta, 90 degrees, and I'm going up. Is that fine? Okay. Now, remember this picture. I can obtain the same picture doing something else. Psi 0, so I'm not rotating this way, theta 90, phi 90. Aha. The Euler angles are not unique anymore. Okay? For every other condition, the Euler angles are unique, which means there's one set of Euler angles that will define the angular attitude of the airplane. Okay? One set of angles. You cannot find a second set of angles that define the same attitude of the airplane. But for this one condition where theta equals 90 degrees, Euler angles are not unique. Let's say another one, like when theta is not equal to 90 degrees. This one here. How do I obtain this? 1, 2, 3. There is no other choice. These three angles are unique. There's no other way I can obtain this. I cannot do first this and then this and then, you know. There's no other choice, right? This, with this sequence, of course. But if theta equals 90 degrees, I can obtain theta equals 90, like this one, this situation, by two different set of Euler angles. One would be first rotation around psi, second around theta, 0 around phi. It's this. Secondly, psi equals 0, theta equals 90, phi equals 90. So I have the same situation. I didn't change the sequence of rotations, right? Psi theta phi, psi 0, theta phi. It's still the same sequence. But they are not unique. In two sets of different Euler angles, I can obtain the same flight condition if theta is equal to 0. So because the Euler angles are not unique anymore, it has to show up somewhere in the mathematics. And that's where it shows up. Because now this is getting confusing, since we don't know anymore in which axis theta phi and psi really are written. Because this and this versus this and this would give you two different results. So this relation is not a one-to-one anymore when theta is equals 90. And therefore, it shows up in the mathematics as theta goes to infinity. Tangent theta goes to infinity when theta equals to 90 degrees. So the answer to my question, what is wrong with this? The answer is that when theta equals 90 degrees, the Euler angles are not unique anymore. In other words, there are a number of sets, or two sets of Euler angles that will constitute the same flight condition. Euler angles are not unique anymore. And therefore, in mathematics, it shows up in places like that, where theta simply gives you, theta 90 degrees will simply give you no solution. I mean, this, going to infinity means really there's no solution. Okay? Very important point. Very, very important point. So let me write it down. At theta equals 90 degrees, the Euler angles become non-unique. There are more than one combination angles that define the aircraft's attitude. And attitude means angular position, right? We know that by now. And I gave you that example. For example, you might go theta equals 90 degrees and phi equals 90 degrees and psi equals 0 versus psi equals minus 90, theta equals plus 90, and phi equals 0 degrees, and it would constitute the same thing. Of course, this is now not nicely written because it looks like they are not in the same order. Let me just rewrite this in the correct order. I apologize. Psi equals 0. Theta equals 90 degrees. And phi equals 90 degrees. Versus psi equals minus 90. Theta equals 90. And phi equals 0. Okay? So they all go in the same order, but a different set of rotations will give you the same attitude. Okay? So therefore, this r over minus 1 will no more hold a relation. Okay. Now, I just must say that this is a consequence. I mean, the fact that this doesn't work is really a consequence of the fact that the Euler angles are not unique. You know, I sometimes ask the students, what is the problem with Euler angles? Is there a problem with Euler angles? And they answer me, tangent theta is 90 degrees, tangent 90 is infinity. I don't know what that means. Don't write stuff like that in the midterm. I will really just get angry and go like, and take my red pen and go like this. Okay? The problem with Euler angles is that when theta is 90 degrees, they become non-unique. Therefore, they will show up in a lot of mathematical places where it goes to infinity. So how do you deal with this problem? So that really means that if the airplane goes to 90 degrees, then you cannot make measurements anymore, right? I mean, look at this. So it means this. If theta sees 90 degrees, look up here. Look up here. If theta sees 90 degrees, you get 90 here. You get infinity. Get infinity, 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 and you're done. This loop will just blow up, right? So what do? What can you do? Avoid 90. When you see 90, don't send 90. Send 89.9 so that you don't blow up. But you know, the computers, they will not like that because you will have a very large number here. It will not be infinity, but it will be very, very large, right? So you don't like that. So what do? Well, here's what we do in real life. I mean, you can do all these tricks. You say, if it comes close to 90, take it 85. When you pass 90, take it 95. You know, you can do all these things. Or if it's a helicopter that will never go 90 degrees, you can still use this relation. Or it's a small little airplane that only does this, never does this, you can still use it. But you need to know when you see 90, you will blow up, right? But in real life, for fighters and things like that, we do something else. And there's a good solution for this. We don't use this relationship for Euler angles, okay? We use a mathematical transformation, which I will not explain in this class. But if you take an INS class, Inertial Navigation Systems, for example, is in graduate level in this department, you can learn about those tricks, let me just say. It is not very sophisticated thing. It is just a mathematical trick in order to avoid the 90 degrees. Instead of theta, phi, and psi to measure the Euler angles, we make a mathematical transformation to theta, phi, and psi. Theta, phi, and psi. We do a mathematical transformation to numbers, to a system that is not really a physical system, it is just a mathematical transformation. We are increasing the number of variables going from here to here. These variables we call quaternions. And we make all our calculations in the world of quaternions. The world of quaternions is a mathematical transformation where this uniqueness does not exist anymore. I mean, if you increase the number of variables, you could intuitively think that some of the uniqueness will go away. And this is exactly what's been done here. And these are here Euler angles, and these are quaternions. And we don't have that non-uniqueness problem. Uniqueness goes away. So basically, all your measurements that you have seen here, you will still measure P, Q, and R, but all this stuff here that you see will be done in the world of quaternions so that this thing never goes to infinity. But at the end, you will get quaternions, and you can transform it into the Euler angles, back into the Euler angles. Okay? So you open any book, any navigation book, and look for quaternions, it will tell you the mathematical relation that will take you from P, Q, and R to quaternions to theta, phi, and psi, and all this. It's not a secret. I mean, some people have written it down. But the quaternions themselves, theta 1, this Q1, Q2, Q3, and Q4, they don't really have physical meanings. Okay? I mean, the way we understand it in terms of angles and things like this. Theta, phi, and psi, the Euler angles, they have a physical meaning. It's a rotation around coordinate systems. They don't. Okay? It is a mathematical transformation to avoid that uniqueness. If you do quaternions, you can do now everything. You can do loops, theta 90 degrees, everything. Okay? So if you want to have a good application of your gyro to calculate this, you need to use quaternions. Okay? Any questions? Non-uniqueness goes away. Any other questions? Okay, one more problem here with this thing. Look, you are doing PQNR, you're doing this, you did this, and then you take the integral and you obtain this. Now, imagine you have a little error in PQNR, in the measurement. Measurement is never perfect, right? You always get an error. Let's say you have an error. Let's say you have a constant error of 10 to the minus 3. Small error, radians per second, 10 to the minus 3, really small. What happens is that, yeah, if you look at it, it's a small error. But you're going here and you're integrating this in time. So which means the error will always come back to this, and slowly by slowly the error will be integrated on top of each other so that the error becomes larger and larger here. In fact, you're taking that error and sending it back here, so this one has now an error, right? You have an error and another error, you obtain this, and then you integrate the error to the previous error, because you're integrating, and this becomes even more error, has even a bigger error. Comes back here, error, 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 you add them on top of each other. So because of this integral, the error of the measurement becomes larger and larger, okay? So, although at the beginning you might have a good measurement, as time goes by, because of this integral, the error will add it on top of each other. So theta, phi, and psi measurements will become worse and worse and worse, okay? This is what we call a gyro drift. The gyro is drifting from giving you the right information, okay? The name gyro drift, of course, also constitutes the fact that in the old times, the gyros were really things that were rotating, okay? That's a whole different story. I would encourage you to go to the web and try to read about how gyroscopes work. The old gyroscopes, they actually had 3 pieces that were rotating, okay? And because of the rotation, you would have friction. And because of that friction, you will have a lot of errors in the measurement, okay? And because of this integral, they will add up, add up, add up, and suddenly everything seems to be a lot erroneous as time goes by. So we call this generally, we call this gyro drifts, which means at the beginning you can find the good angles, but as time goes by, they will get worse. So when I say time goes by, how much time are we talking about? Well, it depends how good your gyro is, of course. If these measurements P, Q, and R are good measurements, I mean, if it's a good gyro, the error will be small, right? And therefore you will hold a little longer, which, I mean, the error will build up, but the acceptable values for theta, phi, and psi will hold on for a little longer. If you have bad measurements over here, this will pile up very fast. So if you have a really good gyro, you could really hold on for a few hours to still have good measurements. If you have a bad gyro, this might only hold for half an hour, 20 minutes, 15 minutes. After that, this will be so erroneous that you need to either land or forget about theta, phi, and psi, or find a way to reinitialize. If you can reinitialize, basically start from 0, so basically resetting all the errors, then that would be also good. Which means if I had another way of measuring theta, phi, and psi every now and then to reinitialize, that would be really good, right? So these are the tricks in instrumentation and in aerospace. Okay? Yes, please.
Can you use some basic control applications to reduce that error, such as PID controllers?
No, controllers cannot do that. Filters sometimes have an estimation. Kalman filters have an estimation of these drifts, or these biases, let's say. But again, it is not, there are, You can do a lot of tricks if you have 3 gyros and 3 accelerometers, because IMU has 3 gyros and 3 accelerometers. You can do a lot of tricks and a lot of estimations. You can estimate the error. If you can estimate the error, then it might help you. Okay? That's why there are so many filter applications, estimation algorithms and all this, to estimate the drift. If you can estimate that, then you can hold maybe another 30 minutes. But there's no solution like that. And controllers certainly cannot do it. Okay? So, any other questions? All right, so that was the fun part. We have one more important topic before we go into finally equations of motion, which is F equals ma, right? We are not still there yet. There's one more topic we need to clear, and that is theorem of Coriolis. You know Coriolis, right? Should be your favorite topic. Theorem of Coriolis. We need to understand this very well, otherwise we will not be able to write the equations of motion in 3D. Okay, so this is a serious topic. Yeah, I know, but that's life. If it's not, nobody will pay you, right? That's the thing about aerospace engineers. I mean, if anything. Imagine in 1 year you will graduate, right? And someone is going to pay you a lot of money. Why? Why would somebody pay you money? They will pay you money for one fact only, that you can do things that other people cannot easily do. If it is too easy to do, then anybody can do it and nobody will pay you, right? There must be a difference between my mom, who likes to cook, and you as an engineer. If you know only the obvious things that my mother knows, then nobody will pay you. So difficult things that are difficult to understand are the key points, are the key areas that you really need to know well, so that somebody will say, theorem of Coriolis, nobody understood, but these 5 guys, they understand it. So we're going to pay them so they do something for us with it. Okay? So therefore, you must be happy that there is something that's difficult to understand, because maybe this is the area where you will be really good and people will pay you even more. Okay? Are you fine with this? Good. Okay, theorem of Coriolis. Now try to understand. Let's say I have an airplane that looks like this. Okay. ZB, YB, XB. And let's say this is the velocity vector of the airplane with respect to Earth. Okay, I've drawn this 1,000 times, but this is what it is. This is equal to, and we plot another airplane. X body, Y body, and Z body. And this is equivalent to, let's do this, right? This is here, the U, so it's approximately here. Right, this is U. And this one here, this is approximately Y. So this is V. And let's say it has a little bit of Z that we don't see. So this is W. Okay, so U, V, and W. So this is what it looks like. Okay, so this way is equal to that. Let's call this 1, U1, V1, W1. So V is equal to U1, V1, W1. Okay? And let's say the airplane now is in a turn. Okay, it's turning a little bit. It's turning a little bit. It keeps turning. So this is now x body. This is z body, and this is y body. Okay? And this is still my velocity vector. Right? It's the same velocity vector, so only angular change. Angular change. So v is still v, it's the same v, okay? Same velocity vector. Okay? Same velocity vector. The direction hasn't changed, the magnitude has not changed, it is still the same velocity vector. Okay? Now, let's try to write this in this form. Right? Let's do the same for this now. The airplane looks like that. Okay, this is x body, z body, and y body. Okay? So let's try to write this. So it will be something like this. There will be something like that. And there will be maybe something like this. So the new velocity vector is now written in this body fixed coordinate system. This is still body and this is still body. And this will be now u2, v2, w2. Is that correct? Right? Understood? I mean, the velocity vector is the same. It doesn't change. I'm writing it in the body fixed coordinate system. Body, 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 body. And here's this one. Is that good? Now here's the question. Are these two u1, v1, w1 and u2, v2, w2 the same? Will they be the same? No, they will not be the same, right? Because the attitude has changed, so they will be different. I mean, you can see it here. There's a lot in the in the x body direction. Now the velocity vector is the same, and this is the CG of the airplane, right? The CG of the airplane, and the CG of the airplane is still doing the same thing, except the coordinate system attitude has changed, and therefore u is no more. u2 is not equal to u1 anymore. It's obvious, isn't it? Yes or no? Yes. Okay. So u1 will change to u2, is it? v1 will change to v2, and w1 will change to w2. Is that okay? You know that they are changing, right? They will not be the same. Do you see that? Because you're going from here to here, okay? And this is equal to that, and this is equal to this. I mean, it's the same airplane. I was trying to plot the same airplanes here and here. I'm just trying to show an airplane that goes from here to there. Okay? So it's basically an airplane that is doing this. I mean, if you look up here for a second. So you have this, in the first picture, look up here, and the second picture you have this. Okay? Basically you have an airplane that does this without changing its velocity. It's just changing direction. It's doing this and doing that. Understood? So you have an airplane that is flying with the same velocity, doing this and doing that. Same velocity. Okay? During this maneuver, look up here. During this maneuver, will u1 and this u1 change in the body axis system? If the velocity vector is the same and it doesn't move, will it change? Yeah, of course. I mean, you see that it's changing, right? I mean, from this picture to that picture, you have seen that u2 is changing because the direction is changing of the coordinate system, but the velocity vector is the same. So u1 and u2 will be different. Velocity vector here, look up here. Velocity vector is this one. Airplane flying like that and rotating like this. Velocity vector is the same direction. Okay? u1 and u2 is changing. v1 is changing to v2. w1 is changing to w2. Is that correct? You agree with it? We have to agree on that. Because the next question will be a little bit more confusing. We understand that they are changing, right? Okay. Is there acceleration on this airplane? translational acceleration. I mean the A. Not talking about the angular or anything. I mean even angular, let's say it's a constant angular. Is there an acceleration on this airplane? Is there? How many people say yes? How many people say no? See, democracy doesn't win again. The answer is no. And we had more people saying yes. Why is there acceleration? Why do you say there's acceleration? The velocity vector of the CG has the same magnitude and the same direction. What is the definition of acceleration? Acceleration only happens when the velocity of the CG changes direction or changes magnitude. Otherwise, there is no acceleration. Look to me strange. Goes back to high school, F equals ma, right? And the acceleration is defined as the time rate of change of the velocity vector. Have a question? Time rate of change of velocity vector, it needs to change direction or magnitude. Is the direction or the magnitude changing of the velocity vector of the airplane? Just tell me now. No, right? I mean, if you have, we either need to give a break or we need to stop. Yes, yeah.
But what about the acceleration caused by rotation?
It might, well, where's the acceleration? Let's say you rotate at a constant angle, constant velocity like that.
Initially, let's say the angular velocity.
Let's say the angular velocity has an acceleration. What about the CG? The angular velocity, listen, A is the acceleration of the CG. F equals ma, listen, F equals ma is only defined for particles, for point masses, what we call point masses. F equals ma is only defined for point masses. If it's a three-dimensional rigid body, we say the rigid body is all represented by a particle, by a point, which is the center of gravity. So F equals ma, the forces, the accelerations, they are all defined for the center of gravity, that point mass. It's not a three-dimensional body. Okay? F equals ma is only defined for the point mass. We will go probably next week. When you go into 3 dimensions, it's a set of particle points, of particles that constitute a 3-dimensional body, and then we will talk about rotations, and that we will call Euler angles. So the total will be Newton-Euler angles. Okay? But when I say F equals ma, and when I talk about this acceleration, I'm talking of the acceleration of the center of gravity only. Okay? Now, the center of gravity moving forward, the airplane is only rotating. When I say acceleration, translational acceleration, I only mean the acceleration of the CG. Is that fine? You had another question.
That was the same question, but I was thinking the Coriolis acceleration has a component of angular velocities too.
I'm not there yet. We'll talk about Coriolis in a minute. I'm just trying to agree on the basics. Meaning that we have an airplane with a velocity vector that looks like that, and the airplane is turning and the velocity vector is not changing magnitude or direction. Do we have an acceleration? No. Okay? So let's agree on that. We don't have an acceleration because the velocity vector is not changing direction. You might be doing this, I don't care. As long as this velocity vector is constant and moving in magnitude and in direction, it doesn't matter what the airplane is doing. The airplane, as far as I'm concerned, has no translational acceleration. I'm not talking about angular acceleration, angular velocities, anything like that. The translational acceleration is 0, ladies and gentlemen. Because the velocity vector of the CG is pointing in the same direction, it's not changing magnitude. Yes?
Can we talk about the acceleration of point right, element-wise actually, for AX, AY, and AZ? Is it possible?
I will come to that in a second. Let's agree on the first thing, because we were not in agreement if this airplane had an acceleration or not. Just want to make sure that everyone understands there's no acceleration here. Translational acceleration. Okay, I will come to your point in a second. Did we all agree? Okay, second question then. If I would have given you these two numbers, these two vectors, listen. If I would have given you these two vectors, changing numbers from 2 to 5, 3 to 10, I don't know. Would you tell me there is a change in acceleration? Without this story, you might say, yes, I mean, the velocity is changing, obviously, and therefore there must be an acceleration, right? Because the numbers are changing. But why are the numbers changing? It is because this is changing. So therefore, looking at the change of the velocity vector itself doesn't tell me the whole story, right? Someone also has to tell me how fast the airplane is rotating so that I can put that somewhere in the equation to say that the airplane has a rotation, therefore maybe this change is not because of the actual acceleration of the airplane, but it might be because, just simply because the coordinate system is rotating. I mean, the reason we will see a change is simply because the coordinate system is rotating, not because the airplane has an actual acceleration, you see? Understand? So somewhere in the equation must be this angular velocity of that airplane so that I can know from where this change in numbers is coming from. Because if I just look from here to here, it looks like it has an acceleration because the numbers are changing. But it is changing because of my attitude change. Okay? So you need one more thing in there that tells me that there's an acceleration or not. Okay? So this is like the idea when we are trying to do this. So looking at this one to this, let's call this 1 and let's call this one 2. I have time? No, we don't have time. So let's give a break. Let's make it, okay, 10 minutes break. 51, I'll see you.